Hi, I'm Professor Goins, and in this video I'm going to describe the geometric idea for a partial derivative. In later videos we'll get to ways of computing partial derivatives more efficiently, but in this video I just want to provide the basic geometric motivation for the definition of a partial derivative. Alright, so let's say I have this surface, z is f of xy, so it's sort of like this magic carpet type surface in 3 space, and those are going to be the same. Think of those as the same graph there, and I want to look at the same point in both of them, so where x is 3 and y is 4 in each of these graphs. So this has the coordinates 3 in the x direction, 4 in the y direction, and then the z values is whatever the function would be at that point. So f of 3, 4. All right, so in order to find a partial derivative, what we're going to do is we're going to turn this into a single variable function. If I fix the value of y equal to 4, then that means that I'm only looking at the points on the graph where y is 4. So that means it would be above the graph above that right there, which would be, think of like that plane where y is 4 intersecting with the curve, and so that would give me, say, that graph right there. So if I fix y equal to 4 and I look at the graph up above that, it's going to be that blue curve, which is going to be a single variable function. So this blue curve would be given by z is equal to f of x 4. Before I do anything with derivatives, let's do a similar thing over here. If I fix x as 3, let's see, I'll use purple this time. If I fix x equal to 3, then I'm going to consider the graph that's only above that. So it's the intersection of the plane x equal to 3 with the surface, and that's going to give me, say, this curve right here. So this curve right here would be z is equal to f of 3 comma y. And we could consider the following tangent lines. We could look at the tangent line that would be tangent to this curve here, or we could consider the tangent line in this direction, this way. So notice that this tangent line right here is going to be parallel to the YZ plane. Or I'm sorry, not the YZ plane, that'd be the XZ plane, because it's going, Y is fixed, so that's going to be coming out of the board. That's going to be parallel to, so it's going to go along that curve. But this one here is going to be parallel to the YZ plane. It's going in that direction. So this is going in the X direction, whereas this one is going in the Y direction. And so here's how we define, or here's how we think of the partial derivatives. So the notation for the partial derivative at that point 3, 4 would be the following. We use what's called a curly D. So df dx, because going in the x direction, evaluated at the point 3, 4. So x is 3, y is 4. The way we think of that is it's going to be the derivative of f of x4. So this is the single ordinary derivative of the function f of x comma 4 with respect to x, because y is fixed, so therefore x is a variable, and then we'll evaluate that when x is equal to 3. So this is just a plain ordinary single or ordinary derivative from Calc 1. And this is what the partial derivative is. So notice I have the 3 and the 4 are plugged. First I plug the 4 in, I differentiate, and then I plug 3 in for x. Over here, similar story. This is going to be the partial derivative of f with respect to y evaluated at the point 3, 4. So notice both of those are evaluated at 3, 4. They're both a derivative, but this has x as my variable, this has y as my variable. And the way we compute it, at least initially until we come up with some more efficient way to do it is I look at the ordinary, the single variable function, f of 3y, and I differentiate that. So this is the derivative of f of 3y. So I fix my x, and then I evaluate that when y is equal to 4. So we're looking at the derivative with respect to x or with respect to y. This means that I'm looking in the x direction, y is fixed. This means I'm looking in the y direction, x is fixed. And so one way to accomplish that is to plug in the corresponding y or x value, differentiate, and then evaluate. So let's do an example to illustrate that. So let's say I have the following multivariable function. Let's say f of xy is x squared y minus x y to the fourth. And let's evaluate the following partial derivative. So let's evaluate df dx at the point 1, 2. And let's do the partial f with respect to y at the same point, 1, 2. For this partial derivative right here, this is going to be this scenario where I'm fixing y, right? I'm going to fix y, and I'm going to think of the function f as a single variable function. So if I wanted to look at the function f of x comma 2, well, I plug 2 in for y, so it's going to be 2y squared minus 2 to the fourth would be 16, so it's minus 16x. And so therefore, the derivative of this function here, so dfx2 dx would be, oh, sorry, I put a y here. This should have been 2x squared. Sorry about that. Because I plugged 2 in for y, so it's 2 times x squared. So sorry about that. Okay, so then the derivative of this would be 4x minus 16. Okay, and putting this together, the partial derivative of f with respect to x at the point 1, 2 is the ordinary derivative of x with y plugged in, evaluated when x is 1. So I take 1 and plug it into this derivative, so it would be 4 minus 16, which would be negative 12. For the second derivative that I want to do here, I should say additional derivative, not a second derivative there, but whatever. So then for this derivative is with respect to y, so that's this scenario here where we're looking in the y direction, right? The x is fixed, y is my variable, and now we can compute that one. So we have, let me separate this here, and what we're going to do is take the partial derivative of f with respect to y evaluated at the point 1, 2 is going to be the ordinary derivative, so df, but I'm plugging in the x value first, so that's going to be the derivative of 1 comma f of 1y with respect to, oh, there's another typo on the board. That should have been a y. My mistake. I apologize for that. In the classroom, people would have yelled at me, but I guess since this is just a YouTube video, it's just me. Okay, so therefore this would be dy evaluated when at the y value, so evaluated when y is 2. All right, well, what is f of 1y? So let's do this over here. F of 1y. What function is that? So I look at the original function that we started with, and I'm going to plug 1 in for x. So that's going to be 1 squared y, which is y, minus 1 times y to the fourth, which would be y to the fourth. So I take the derivative of this and then evaluate it when y is 2. All right, so when I differentiate this function right here, I get 1 minus 4y to the third. Evaluate when y is 2. So I get 1 minus 4 times, when I plug it in, that would be 8. So 4 and 8 would be 32, so this would be 1 minus 32, so minus 31. So the derivative at that same point, 1, 2, is different if I look at it in different directions. So if I look in the x direction or I look in the y direction. Okay. If you're wondering, well, if I'm on this surface and I'm standing at that point and I'm looking at the slope in the x direction or the y direction, I could look at it in other directions too. For example, I could look at it in maybe not exactly along the x-axis, but maybe if I look at it sort of in this direction or this direction, that direction, any direction, I could have a slope. So there's actually infinitely many different directions that we could stand on or look in, and we only have the x and the y axis. How could we do that? How could we look at a slope in a different direction? Well, watch the video on directional derivatives and we will describe exactly that.